Okay, so we go back after a short break. As I said, I'm going to define a certain example of simple random walk. It takes place on the surface related to certain irrational number alpha. The definition is as follows. First of all, we choose a place where to start, and the starting point is chosen according to uniform distribution. So we pick random the point. Okay. And now we flip per coin. If the result is S, we move to the point. Our new point is x0 rotated of angle alpha. I use the additive notation. And if the result is S, our new point is the point x0 rotated of angle minus. So both these takes property 1/2. And that's our new point, depending on what one of these 2 points is our new point, depending on what was the result. This random, the question is whether the first point is chosen according to, well, so that the x0 is the first point, then we get x1, and then we repeat the procedure with respect to our new point x1, and this way we obtain a stochastic plot with the Markov plot, the same. In other words, this is a iterated function systems with 2 rotations, angle alpha and minus alpha, so it is 1/2. The question is why we should distribute the first point according to the Lebesgue measure, and the answer is that then the process is stationary. Which means that xn is the distribution of xn, our position after n steps, is also given by the Lebesgue measure. Birkhoff-Egoli theorem implies that for every function phi that is integrable with respect to the Lebesgue measure, we have phi of x1 and tends almost surely to the integral of phi with respect to the Lebesgue measure. Actually, from Birkhoff-Egoli theorem, it follows just that it converges to something, to some limit, and this limits. This follows also from the ergodicity of Lebesgue measure, I mean, which I didn't like to justify, but that's true. Okay. The question is that is Lebesgue measure the unique stationary measure for this random walk? In other words, can we choose the distribution of x0 in some other way, in such a way such that the resulting process is stationary again? And the answer is no, and it's very easy to show. But maybe let me not concentrate on this. It's important that it's a very simple system, and we can ask some questions about more complicated statistical behavior. For example, central limit theorem. So, is it true that central limit theorem holds? It means that probability is some subset of the form A. Sorry. Probability that the Birkhoff average after n steps is in some interval of this form should be more or less independent of and should converge to something, and the something is the integral over interval AB, and here it should be normal distribution. And we assume here, of course, that the integral is equal to 0. So that's the question. Is it true that central limit theorem holds? Well, it's quite clear that it should depend on the regularity of observable phi. Yeah. But it also depends on number theoretic properties of the angle of rotation. So it's quite easy to show that if phi is small, maybe I have to define what angle the Diophantine dual angle is. So definition, alpha is Diophantine times gamma if for every PQ alpha minus P over Q C over Q to the power n. So it means that the angle alpha is not well approximated by rational numbers. So if you consider dynamics, if you have rotation of angle alpha, then this rotation cannot be too close to rotation of rational angle. Okay?
Can you describe again the process?
The process. The first step would be randomly. We start with x0. We choose it randomly with uniform distribution. Then if x0 is chosen, then we can, the next step, we can move to 2 points. x0 rotated of angle minus alpha, and x0 rotated of angle plus. And each one is chosen for probability 1/2.
And this you call x1?
Sorry?
And this is x1?
Yeah, this is
Okay.
x1.
I understood. Okay.
And now we call angle u if it's just not there. That's simple. We can it can be quite easily shown that if phi is small and alpha is Diophantine of type C gamma, let me write that in this way. Then central limit theorem holds. And that's quite easy to prove. It's not so difficult. There is more difficult to prove that if angle is Liouville, then there exists phi that is small and such that CLT fails. That's the first main theorem that I wanted to say about that without any further details. I just wanted to you to know that if you consider such a system with constant probabilities, then its analysis is quite simple, and we can talk about quite advanced statistical properties. And second of all, that there is a strong, the behavior between the distance, the difference between the behavior in Diophantine and middle case is very big. So we should think of that the angle is Diophantine. Then it leads to some regular behavior, and the angle is Liouville and leads to some irregularities. Okay. Now let me move forward to the definition of something that we call after Sinai simple symmetric random walk, simple random walk in general. To define it, we need to pick some function on the circle. Let me now represent the circle in this way. This function should be between 0 and 1. Okay. Small real function. And now, I denote it by P. And now, what is the difference with this random number? Now we fix some starting point, X, it's not given randomly. And now, on this picture, we are somewhat cubes, say. And here, we have some value P of X. Now, again, in next moment, we can be two points. We can just two possibilities. X0 minus alpha and X0 plus alpha. The difference is that the probability distribution is different. So we move to X0 plus alpha with probability P of X, and here with probability Q of X, where Q is just defined as 1 minus P of X. This is something that was investigated by Sinai, called simple random walk. We call this random walk, we call actually P symmetric. If the integral by respect to the Lebesgue measure is 0. And if this condition is not satisfied, then we call P asymmetric. So the definition is very simple. Maybe it's hard to understand why to introduce it or why it's useful, but I will explain that later. And now, Sinai defined this random walk in some paper in Journal of Statistical Physics in 1999. And he proved the following theorem. Here, again, we ask, first of all, we can ask about the distance of stationary distribution, but it's quite easy because it can be proven, existence can be proven using two of our technique. So it's quite standard to prove the existence of stationary distribution. X0 can be distributed. P can be distributed randomly in such a way that the process is stationary. But the question is if this stationary distribution is unique, and it's already very hard to prove. So you see, it's very small difference between this and this, but the system is much more complicated. And now, so this talk is actually about unique ergodicity of stationary distribution for this random walk. And what's my proof is the following. If P is smooth, and asymmetric, then we have uniqueness. Okay, so if this condition is not satisfied, no matter what angle is, we assume it's irrational, of course, then stationary distribution is unique. We can make the process is stationary in just one way. You prove also in the same paper, yeah. You prove that if P smooth is symmetric, and alpha is Diophantine, then you get uniqueness, the stationary distribution. And the main results of mine that I want to present today and talk about is if P is C1 and symmetric. Then we have uniqueness. No matter what angle is, it should be just irrational. Okay. So maybe let me erase the first one.
Something now about properties of this stationary distribution. Sinai.
Yes. That's a good question. We know that, but I will answer for a moment. Actually, we know that in these two cases, stationary distributions are totally continuous with respect to the relative, and we can write down explicitly formula for the density. Actually, we have very simple characterization where when stationary distribution is absolutely continuous, it holds if and only if P is asymmetric or P is symmetric and certain topological equation can be solved. Actually, this proof of theorem 2 also is true in that case, but it's simple to formulate that in that way. Actually, I would like to now say something about this.
And we have a request from the audience to write bigger.
Bigger, okay. Yeah, I was expecting this. I will try. So some remarks about Sinai's proof. Let's define the function f of x as the natural logarithm of p of x by q of x. Actually, I would like to discuss this proof only in symmetric case. In asymmetric, the idea is more or less the same, but it's still qualitatively different. So I would like to discuss only symmetric case. The whole talk is about symmetry. From symmetry assumption, we know that the integral of f of x equals 0. And now I can write down the cohomological equation. That's the equation that's the equation of the form f of x g x plus alpha minus g of x. And so f is known as this function, and we look for function g. And here, if we look for the solution of cohomological equation, then the integral of f should be 0. It's a necessary condition. Why? Because if the solution exists and we have this kind of relation, then we can take the integral on both sides with respect to the Lebesgue measure. And because Lebesgue measure is rotation invariant, the integral on the right hand side will be 0. Because of this form. So on the left hand side, the integral also should be 0. So this condition is necessary if we want to solve the cohomological equation. And now, let's assume the solution exists. It is true, for example, when f is smooth and alpha is Diophantine. You solve it just by comparing Fourier coefficients of both sides. You can write down explicitly formula for the Fourier coefficients of G, and then we just need to check that this function is really a function, but it's not measurable. So that's a bit further. But we know that in our case, so if f is smooth and alpha is Diophantine, there exists a solution of this equation that is smooth. So there exists a smooth solution. And in that case, we can define h of x to be x of g, so the solution. And this can be replaced as q of x by q of x is equal to h of x. Or something like this. It's important that using this property, we can show that h of x divided by q of x is an invariant density. Okay. As I said, we don't. We have in this case we have explicit formula for how this measure looks like. So to put the unique ergodicity, we just need to show that if we have to fix any point in the circle, starting point, and consider the process starting from this point x, then probability that this process starting from x after n steps is say some open interval u should tend to the integral of u on the density. Sorry. Okay. And that is what Sinai does. But how to prove this? We observe that if our starting point is 6, we can write down, draw here the orbit, the whole orbit of rotation, actually of x under the action of rotation, and so on. If we know that the process starts from x, then we also know that it's almost surely contained in this trajectory. Okay? Countable set. This countable set is indexed by integers. So in fact, we have a random walk of integers. So say 0, 1, 2, minus 1. From 0, you move here to probability p of x. Here q of x. That's 3. So here it will be q of x plus 3 alpha. And to the right, probability p of x plus 3 alpha, and so on. Yeah? So that's, I hope that's clear. Integers parameterize trajectory, so in fact we have random open integers. If you have this kind of random walk, then you can show, try to investigate random walk here. Let me denote it by here, by sign. Check what is its distribution, and then deduce something about the distribution of the circle. Sinai proves local limit theorem for this random walk. Local limit theorem, which says that, well, we are interested in this. We want to know what is the value of this, and of course, if you can write down formula, but it says that nothing because it's very complicated and ugly. So what you want to know is some asymptotic formula. We're not interested in the exact value, but just how fast does it decay. And it turns out But it behaves like h of x plus m alpha by q of x plus m alpha. So that's our density, in fact, yeah? And here is sorry for that.
Wait, so better you shift to one side. If you want, so let's move to the next one.
Okay, let me do.
No.
H of x plus m alpha by q of x plus m alpha times e minus m squared to sigma squared to n sigma squared times 1 over 2 pi sigma squared, yes, for some positive sigma. So it decays to 0, it's not, it's decays to 0 clearly with this rate. Yeah, okay. And then Sinai comments that it's actually easy to deduce from this property that uniqueness of stationary distribution, or that this condition is then true. Well, I'm not sure if that's obvious, but it's quite easy to deduce that now. If we put these numbers here on the trajectory, then we convert this to the measure that is absolutely continuous velocity that I measure with this density. So that's Sinai's idea. And now let me comment something about this symmetry and asymmetry condition. What does it mean? Well, so if we consider a random walk just with constant probabilities on integers, so here we down probability p, and here with q, and that's independent. These numbers are independent of the number. Then that's the standard random walk, and you can find everything about the standard random walk in further textbook and probability. If p is greater than q, then actually we write we can jump to the right hand side with probability higher than to the left. It can be replaced by natural log q over q is greater than 0. And in that case, we tend almost surely to infinity. If p is less than q, then we have analogous behavior, but then we tend almost surely to minus infinity. And if p is equal to q, and if it's natural logarithm of q over q, then it's equal to 0. So that's corresponding to symmetric case. Then we know that the random walk is recurrent. So if we start from 0, then we go back infinity many times to 0. Yeah. Observe that using this, we can show that natural logarithm of here is say n plus 1 p of x, q of x, x plus n alpha by q x plus n alpha. By Dolgopyat theorem, it should be close to 0 for n large. So we can think of it as if we take very large block, then the behavior of our random walk in symmetric case could be more or less like this in the symmetric case. So it should be recurrent and so on. It can be proven that in a symmetric case, it behaves like this. So in a symmetric case, it tends to at infinity or minus infinity almost surely. But in symmetric case, maybe it's more complicated, but it also can be proven that the fundamental is to be recurrent and with certain properties. This. Okay.
And so
Mhm.
this and the very easy to finish the proof. Let's say we know that P over Q is bigger than 0. Then we are in the asymmetric case, but very simple asymmetric case.
Yes.
And then we immediately we get the uniqueness.
Well, if we have this case where probabilities are constant, well then actually in this case we don't have to follow this path. So it can be proven exactly the same way as for this random walk that I defined in the beginning. But also, this path actually is also leads to the conclusion. Then I have just to write down local limit theorem, the Laplace limit theorem, very standard thing, and somehow I can deduce using the Laplace theorem the uniqueness of stationary distributions. But it can be done much easier.
Then it's tensional distribution is Lebesgue.
Yes, in this case also the stationary distribution is Lebesgue. Now, so if we want to prove uniqueness, what should we do? We cannot follow this strategy. Why? Because the meeting Dolgopyat and Fayad and M Saprykina have proven that if you take alpha u, so it's our object of interest, alpha is usual angle, then for typical smooth symmetric P probability function, there is no central limit theorem, no annealed, neither annealed nor quenched. The behavior is very irregular. So it's too strong. It's far too strong to prove uniqueness for stationary distribution for a given case. So how to fix this? We can use some other criterion. If we put uniqueness of stationary distribution, then we are usually better with our averages. So let me write the following criterion. If what I'm writing is true, then uniqueness of stationary distribution follows. Continuous. There exists infinitely many ends such that the average. And here I have the process starting from x. Okay, I have 2 points, one function. And I take on expected value of Markov averages on trajectories of the process starting from x. And it should be close to Markov averages of the process starting from y. Well, we know what should be here. And this should be less than epsilon. If this condition is satisfied, then uniqueness follows. That's clear? Yeah. Here it should be phi, x, and y. Why? Because if you have 2 algebraic stationary distributions, then we have 2 points. One is typical. Actually, you can find a function that is continuous and distinguishes 2 measures So the integral, the integrals are different. And then we consider two properties. One starting from the point that is generic for one measure, and the second one is generic for the second measure. So from Birkhoff ergodic theorem, we get that this should be closed to the integral of phi with respect to one measure. This should be close to the integral with respect to the second measure, but this contradicts this criterion because we have a for every epsilon, it can be made a small for infinity many ends. So it's much weaker than Sinai condition. Sinai proves that the expected value of something like this converges to something that is independent on steps. So Sinai uses something much stronger. Okay. So now we are interested in. We have some probability function P and we move to our random open integers. Because we are interested in the general averages, it's natural to ask on the behavior of the limit of expression of this form, psi n x. For finite state Markov chains that are very nice, this convergence to the value of stationary distribution that is given by the eigenvector of Diophantine theorem. So for finite state Markov chain, it tends nice Markov chains on finite state space. It tends to something nice that is positive. The same is true for positive recurrent Markov chains. But our random walk is null recurrent. So we know that this tends to 0 for every state. Okay. Expressions of this type were an object of interest of Kolmogorov, and I think that he was the person who proved this kind of limit theorems for Markov chains in 1936. And here's the question. Okay, if our random walk is now recurrent, we know that this tends to 0 for every state n. But is it true maybe scary, but this tends to 0, but is it true that if I take two states M and K and look on this ratio, does it convert this to somewhere or not? Something. So question Kolmogorov writes this question in 1956, and the answer was given by Berlin 2 years later, who proved that yes, it converges to something. But he didn't identify the limits. By the way, Berlin was it was 1938, and he was then 23, and he died 2 years later in the age of 25. Committed to suicide. So nevertheless, we have several important theorems. So he didn't identify this limit. It was done by Chung, and he said that if you want to find what is the value of this limit, then you should take a look on the process starting from state K. Okay, I always all the time talking about recurrent case. So you have state K and state N. You consider the process starting from N. This process is recurrent, so it goes somewhere and go back. And you take a look on the first moment when you go back, and take a look on this path. You need to see how much time have you been in N before you go back to K. compute the expectation, and that's this value. So it's the expected value of appearances of the process in M, starting from K before we go back. It would be nice to find these numbers for our process, and it turns out that we have a very nice formula. So,
can you remind which case you consider?
I saw
that it was symmetric, asymmetric,
Symmetric.
current.
symmetric, and it means recurrent. It can be proven that it's recurrent. So the proof is the mode to symmetric case, and in that case, the random mode is recurrent. And it's not recurrent, so the expected time of first return is infinite. It takes a long time to go back. We know that this converges in the limit, and this limit can be described by following number. We define ax0 when you pick some x. Ax0 to be 1. Ax1 is equal to p of x by q of x plus alpha. And okay, greater than 1, it's here it should be p of x plus alpha, p of x plus alpha. Times 1 over q x plus k alpha. To define for k negative, we just need to do something symmetric, but we don't need this. This ratio that was on the right hand side converges to the limit given by the ax m by ax k. Okay. So let me maybe remark also axk can be rewritten as something like q of x by q of x plus k alpha exponent, and here is b for coverage f of x, where f was just the logarithm of p of x by q of x. If the solution of cohomological equation exists, then this before sum can be replaced by g of x plus k alpha minus b of x. And the exponent of g was our h, which was related somehow to the density. So, I wanted to point out that this is somehow related. If in the case of symmetric random walk, when we have the solution of cohomological equation, then here we actually see the formula for invariant density. But let me maybe not try to convince you. Okay. Now, how to deduce the theorem? Using that in ratio limit theorem. Let's take continuous function t. Q is well, that may be confusing. But they have to some first return time. Closest return time. Population rotation, rotation of angle. Let us define AK to be interval of integers of the form KQ K plus 1Q. Let us define function phi K, real function in integers. By the formula phi K of J is equal to characteristic function of AK times phi of X plus J alpha. Okay. And now the process starts X. This is equal to sum over all K integer expected value of phi K, and here I put the process starting from X related to X. The process on integers. Because of Devlin ratio limit theorem, we can, for if K is fixed, well, we know that this decays like expected value X, Y, expected value and times the limit that is in the appears in the definition limit theorem. And this limit is something of the box like here times sum over all J and AK phi K of J A X J X J. Okay. I claim that using using that in regular limit theorem, you can easily deduce that this for k peaks, at least for k peaks, this behaves like this problem. I should here also put something because we need to take care about the rate of convergence in the daily ratio limit theorem. So here is some factor of the form n minus n0, and here I should get k. Now k is the moment of the pure visiting interval ak. And it's not so much important. It can easily be proven to not we start on our book, but what really difficult happens is here, because we can prove that it actually up to some epsilon for large q, it doesn't depend on the interval and on x. So this is up to epsilon, that's the same value for all AKs. Okay. And that's something difficult. Let me define mu x q to be sum minus 1 ax, okay, the x plus k alpha, and here should be some dividing factor so that the measure is coordinate measure. We can prove. So this number here is actually the integral of phi with respect to some measure of this type. And the key proposition is the following: that for every epsilon, for every phi continuous, there exists n such that for every q greater than n that is closest to zero time, and for every x, y in t, so in the circle, the integral of phi with respect to d mu x q mu phi q, this value is less than epsilon. So we define certain measure on the circle that depends on the starting point, and it has q atoms. And we show that if q is sufficiently large, then this integral, these two integrals are close to each other. And this actually suffices to conclude the proof, because then, as I said, that's this expression is integral of function phi respect to certain measure of this type.
So why did you assume C1? Here it seems you're working with C.
Yes, but to prove this, I need assumption that P is C1 to prove this.
This last proposition.
Yeah, here, exactly. There's only one point when I need this assumption. Otherwise, some absolutely continuous functions is sufficient.
In this case, in the symmetric homological case in Sinai's proof, does he also use C integral? Or
No, if yeah,
this case,
that's one he doesn't require so strong assumption, but he just don't want to care about numbers. Something. Okay. Maybe. Okay, I think that's this is very technical. So. But okay, that's really the curve of the proof. I have this measure. They should please say something about the proposition. The definition of a I will need that in a moment. Okay, once more. Scan is plus okay alpha e to s k minus 1 that's the average of x of f in the point start the point x, and measure is defined by this formula. Is that visible to everybody?
No, they can only see half.
Yeah.
They have no visual.
Okay. Yes. Okay, alpha times normalizing. We should prove that that's the key point. We should prove that if we have two such measures, x and y, something that x and y have similar length, then these measures should be similar to each other. And this follows, first of all, we can consider the case. Here we take first return, closest return path, okay? So in that case, if we take a look at the trajectory of the irrational rotation, it divides the circle into more or less parts of length like 1/2. Okay. So it's reasonable first to ask, okay, if we take 2 points that are close, like 1/q, then is it true that mu x q is close to mu x y q? And the answer is yes, and that's exactly the point where we use the assumption that P is C1. Why? Because S and F minus S and F y is equal to S and F prime of psi for some point by Nicolaus theorem x minus y. And because this distance is less than 1/q, then actually I can put inequality. And here I can put 1/q. And now, because f prime is continuous, we know that Birkhoff averages, that's Birkhoff average for the action of rotated by rotation, so that's just dynamical system, standard dynamical system, not random. We know that the Birkhoff averages tend to the integral of uniformity. It follows from continuity of this function and from unique ergodicity of the vector. So we know that if n is sufficiently large, say n is greater than some capital N, then by Birkhoff theorem, this is close to 0. Yeah. I could write that this is. I can rewrite that in this one. And n is not greater than q. So this is always less or equal to 1, and by Diophantine theorem, by uniform convergence to Diophantine theorem, this tends to 0 uniformly inside. And here is the moment that we use the assumption that f prime is continuous, so that is C1. If n is not greater than capital N, then actually if Q is sufficiently large, then this is the factor that makes this expression very small. But really, what is important is Q. So because we have something like this estimate, so we know that it can be made less than epsilon if n is sufficiently large, actually if Q is sufficiently large. Then taking blue here, then we know that Ax k is like 1 plus epsilon and yk in the same sheet. So it and because our measure is of this form, it actually proves the proposition. And here is the point where we use assumption that is C1. Then we have somehow to deal with the case where x and y are far from each other. And could this end? Well, let me draw a picture. Five, 8, 11. So that's rotation of angle of the form 1 over 2 plus 1 over 1 plus 3 plus something. So let's say that 0 is our point. We start from here. And we take some other point. We take some other point like here. So let's start from x. We move 1, 0, 1, 2, 3, 4, 5, 6. And that's important moment because this point of trajectory of x approaches y with accuracy 1 over q. Okay. So we define t to be such index that x plus t alpha minus y is less than 1 over q. And then we decompose this measure u x q as a convex combination of two measures. One is m x t, and the second one is m x plus t alpha, and here is q minus t. So this measure is concentrated on the trajectory until we approach moment t, and that's the remaining part. And here I should write some formulas so that it's really complex combination, but I'm not going to do this. And similarly, we can decompose the measure starting from y. Yeah, and then we just need to show. Then we know that here is x t. It starts to be open. mu y q is something mu y q minus c, that's something mu y plus q minus c alpha t. And now, because y is close to x plus t alpha, we know that this measure is similar, is close to this measure. And because x is close to y plus q minus t alpha, we know that this measure is close. So we only need to deal with comparing these coefficients here. This coefficient that appears here should be close to this here, and here is the same. But that's really it's difficult and quite complicated, but not so difficult. At some point, we just need to use Benjamin functional inequality. Let me not go into details. That's this sketch. It's sufficiently complicated now, and maybe let me proceed to some remarks. Well, first of all, you can so it would complete the proof of proposition, and I somehow tried to justify that if we have this proposition, then the periodicity follows. Well, okay. Some final remarks. You can ask if this proof works in a symmetric case, and why not? The reason it doesn't work, and I could write down a similar proof with the same strategy for asymmetric case, but in that derivation theorem, these two cases are completely different. So the derivation theorem holds, but the proof is different in recurrent case and in trailing case. So we would just complexify just the written version of this proof without new ideas. There's also a question about stability. Let me just mention that it's rather general remark about the rate limit theorems. Sorry. We can ask if such a convergence holds. The Devlin ratio limit theorem says that if I take general averages of such expressions, then the ratio is convergence. It's convergent, but we can ask about something like this. And it not holds in general. It was proven by Orey, Kingsman, by Book that this is true for quite wide class of Markov processes, but it doesn't hold in general. In our case, I think it works, and it can be used, to prove stability of the process. But it's again quite complicated technically, and
but could you define what do you mean by stability?
Stability. By stability, I mean that on the process. So on the circle, we take a look on the circle. Process is stable if for every x this converges. It should be uniquely algebraic, and then it should tend to the integral of phi with respect to stationary distribution. From Diophantine theorem, I know that this converges in average. General averages of such expressions tend to the integral. Stability is stronger. It says that this tends to the integral of phi, And moreover, well, it was the strategy of Sinai. Sinai was working with this kind of, he proves stability that is stronger than the uniqueness. So stability means that it stands for. So if you want to prove stability in our case, I haven't done it, then we should take a look on expressions of this form. And it's quite interesting to remark. It was, this kind of theorems are not so popular, I think, and I had some trouble with finding this. But recently it gained attention because of random walks on infinite groups where it is used. When you don't have local limit theorem, you can prove something like this. Third remark is that I don't know anything about the Hausdorff dynamics, this unique stationary distribution. Fourth remark is that instead of derivation limit theorem, I would could use very general Chapman-Orson ergodic theorem. But maybe I don't go into details. If you don't know what the Chapman-Orson theorem is, see it later. But there is an interesting question if it's optimal, this condition. P is C1, is it optimal or not? Can we provide another example? I think that yes, but it would be very technical. So I think my guess is that this condition is optimal. And we cannot improve it. But I don't have even an idea of the construction. Okay, so maybe let me here. Thank you for that. Sorry for complex presentation. Thank you.
Are there any questions? Maybe from the online. Any questions in the online? Please.
Maybe I ask you just very naive question. Are there any interesting ways how to generalize this to kind of works on like torus in kind of dimensional torus? How to go in this way?
Where the original Sinai was on torus. Yes, it can be done. In the case of torus, it's not very difficult. I don't think that there are some important changes. So I could, write everything with small change, putting here some dimension, positive greater than 1, and it still would work, I think. Yes, but well, there are some papers like by Sinai about which drug is included. Okay. That's okay. That you have anorthogonal homomorphism on some space, and you from point X you can move to point X, and for A inverse X we call it P of X and P1 minus X. But I don't know the content exactly, so maybe let me go with this. And by the way, I was interested in the question if for such a systems there exists a stationary distribution of that Markov process, there exists a stationary distribution that is absolutely continuous with respect to volume measure. I don't think that this question is to be answered. We did it on the result.
But how about your case? But when you don't know, right?
In my case, I
mean, symmetric case, right?
in symmetric case, I can write in symmetric case, station absolute continuity, yes?
Yes.
Then going back to the beginning of the talk, I wrote the homological equation, g of x plus alpha minus g of x, where f was the ratio of logarithm of p, and one can show that there exists stationary distribution, meaning stationary distribution is absolutely continuous with respect to the measure p, and only this homological equation is a solution.
And then this is this H over Q.
Yes.
Are there any other questions? Okay, so if not, let's send this to the exam. Very interesting.
Other new Znaczy, nie, no tam, to jest trochę tam zagubiłem w tym momencie, o których